I mean, but you could also kind of, I mean, yeah. So here's an easy thing that if you're looking at Sn plus 1 minus Sn. Right? Well, Sn plus 1, or Sn, say, this here was just, right, this here was just C to the power 0 up to C to the power n. Sn plus 1 is where you do the same stuff. You're adding these guys, but then you have to add one more, right? So this means that this difference here is really C to the n plus 1, right? But now I could look at the absolute value of this difference. This is this. But this is the same, again, as C to the power n plus 1. But you see, if C here is, the absolute value is bigger or equal to 1, then this thing here, so if the absolute value here is bigger or equal to 1, then this thing here must be bigger or equal to 1. Right? Remember that if a sequence is convergent, then it is a Cauchy sequence. It's a Cauchy sequence that if you go sufficiently far out, then from there on and out, everything bunch very, very close together. But you see here, not even two consecutive is bunching together, because independent on how far out, how large n is, the difference is always at least 1. Right? So this is not even a Cauchy. I mean, it's actually equivalent, of course, but it's not a Cauchy sequence. It sort of failed. Like the most basic thing with consecutive ones does not even lie close together. So this proves this theorem about the geometric convergence, the geometric series convergence. Okay. So now, so this is like the most important example of a sequence. Maybe the second most important is what's called the harmonic series. So, harmonic series. But the harmonic series is unfortunately not a series that is convergent. So the harmonic series is the following. So again, I'm writing it, I'm using this abusive notation that I'm writing the series as like an infinite sum. But this infinite sum, but it's not a convergent series. So the infinite sum doesn't really make sense. So this is the, here I have to start because I'm dividing by n, so I'm starting by 1 with 1. So this here is called the harmonic series. Okay, and there's various, so for series there's like a sort of bunch of things, bunch of tests that are useful to determine whether a series is converging or not, right? And we'll talk about these tests. I'll talk a little bit about later in this lecture. I'll talk about some of the tests, but not all of them, and we will later talk about more. The test that is particularly useful in this case, it's what's called the integral test, but I won't talk about that today. But instead, I will show you a very simple proof of why this here is not convergent. So here's a theorem. The harmonic series is a divergent. So it's not convergent, it's divergent. Okay, and so in fact, what we will prove is the following, that we will show that if you're looking at, so n is an integer, if you're looking at so this is like this is only sum of the, you only hit for this here you only hit some of the elements in the sequence, right? So this is where I'm summing again from I equal to 1 to 2n to 2 to the n minus 1, n is an integer, of 1 over I, right? So I want to prove that these guys here, if the original sequence has been convergent, then of course any subsequence would also be convergent. And we're going to prove that this thing here is bigger or equal to n over 2. So I claim that we have this. So this is a claim. That you have this, but if you have this thing here, you see that then this subsequence here is unbounded, right? So of course the original harmonic series is not convergent, right? So let's try to prove this. And again, you know, this is not, this is just like a simple proof of that, very simple-minded proof that the harmonic series is divergent, but there are, you know, more, you know, once we learn about the integral test and so on, there are other, in a way, better ways of doing it. So let me try to prove this. So I want to prove the claim. Proof of the claim. So I'm going to prove it, right? So I just prove, so I want to establish this for all n, and I'm going to prove it first when n is equal to 1, right? So let's show this for n equal to 1. So for n equal to 1, well then the claim here means that, right, so 2 to the 1, that's 2. So this is S1, right? Right, because 2 to the 1 is 2 minus 1, so this is 1. So I claim that, so I want to prove that S1 is bigger or equal to a half. I want to show. But of course, S1 here, S1 is just 1 over 1. So it's actually, that's definitely fine. Okay? So this is, so it's for, so we want to prove the claim, and the claim is okay. So claim is okay for n equal to 1. Okay? So now I want to prove it. So I want to assume, assume the claim is correct for n, and we want to prove it want to show it, to show the claim for the next one, right? And so I have that, so we assume that S2n minus 1, that this is bigger than n over 2. And then I want to look at S2n plus 1 minus 1. Okay, how can I write this thing here? So I'm summing, right? This here is a sum of the 1 over I where I do it up to this thing here. But I can think about that as the sum of the 1 where I do up to this here. And then I have to, sum the rest also. So this is I equal to 2n to 2n plus 1. 2n, plus 1 minus 1. Like this, of 1 over I, right? But now you see, I want to bound it from below, right? So I have, so if you sort of continue this line, then by assumption, this thing here is bounded by n over 2, right? This thing here, right? I'm summing, right? I'm summing two n numbers, right? From here to here, there are two n numbers, right? And so it's two n numbers, and if I take the smallest of those two numbers, right? If I take the smallest of these guys and I multiply it by 2n, then that's definitely a lower bound. So let's try to do this. So I say 2n, 2 to the n, and then the smallest, but the smallest is the last one. So the smallest is 1 over 2 to the n plus 1 minus 1, right? But this thing here, right, is of course obviously bigger than, so n over 2. This thing here, well, this is 2 to the n, but this thing here, if I divide by a larger number, and the larger number is just this here, then I get something even smaller. So I would have 1 over 2 to the n plus 1, right? But now you see that this thing here cancel with these guys here, and so you're getting that this is n over 2 plus a half, and so this is n plus 1 over 2, and that's exactly the claim for n plus 1. Right? So we've proven that if it was true for n, then it's also true for n plus 1, and we remember to check that the beginning was also okay. Okay, so that's the harmonic series. So you see that the harmonic series is divergent. Now, the harmonic series is, of course, an example of something else. Namely that if you're looking at, so when you're looking at a series, the first thing you look at typically is okay, so let me just have a side here. So if you give me a series, you know, it doesn't really matter where, I mean, it doesn't matter very much where it's, for whether a series is convergent, it doesn't matter where you start, because this is just adding something to it. It will matter where you start for the limit, but not whether or not the series is converging. But if you give me a limit, the first thing I always check is that this, so first, so for a series, always check if an goes to 0 or not. And why? Because if you give me a series, the question about a series is always whether it's converging or not. Right? And again, just like we did, if you're looking at Sn, say, minus Sn minus 1, this is where I'm looking at two consecutive things, right? But if I'm looking at this difference here, the difference here, this is where I'm summing up to the an minus 1. Here I'm summing up to the an, so the difference here is an. And if the sequence, just like we saw, if the sequence of the series, is convergent, it means that this sequence here is convergent. But it means that it has to be a Cauchy sequence, that things have to bunch together, but that two consecutive bunch together or not is determined whether an goes to 0 or not. So if an does not go to 0, you're already done, right? There's no reason to continue. It's already clear that this, if an does not go to 0, you can just say it doesn't converge because an doesn't go to 0. So there's no reason to start with any kind of test or anything, any sort of good ideas. Okay, so that was just a side remark. The other thing is that for the harmonic series is, so this of course failed this test. But it also is an example of something where you're taking, so suppose you take so you have a sequence an, and then you're forming the series. This series here. Now, if all of the ANs, suppose that all of the ANs are non-negative, right? Then if you're looking at Sn plus 1, you can think about Sn plus 1 as where you're summing the first n elements, and then you're adding the n plus 1 element, right? So this here you can think about as Sn plus An plus 1. And so, of course, if all of these elements is non-negative, this means that this here is non-negative, so this thing here is bigger than Sn. So you see that if all of the element An is non-negative, then this sequence Sn is monotone. So in this case here, if you have this implies that this Sn is monotone increasing. Right? And so now to say whether this, if you have this, to determine whether this series here is convergent or not, it's just a matter of proving whether, to determine whether this sequence is bounded or not. Right? So you just need to find a bound. Okay. So this naturally leads to looking at what's called absolute convergence. So this is something stronger than convergence. And for many things, although not all, there's a particular test that deals with it, where you don't have both things, or where you don't have the stronger property. So for many things, you have absolute convergence. Okay, and so let me try to, so absolute convergence. So again, you have a series here. This series here is said to be absolute convergence or converge absolutely. So converge absolutely. If the series where you slap absolute values on them, if this thing here converge. Right. So if this, so we say that this here converges absolutely if this here converge. Okay. Now, so I claim that that absolute convergence is stronger than convergence. So absolute convergence implies convergence. So this is a theorem. But it's not the other way around, right? So if you have what's called so here an example. And we haven't yet proved that it's converging, but we'll do that in some later lecture. So here's an example. If you're looking at the series minus 1 to the power n divided by n equal to 1 to infinity. This here, you see, this is, if this here just had been 1, then it had been the harmonic series. This here series is also kind of like a famous series. It's called the alternating harmonic series. And it's alternating. Alternating means that the sign of it is alternating, right? So the sign of this AN element, it keeps changing from, I guess in this case, the first one is negative, the next one is positive. So it goes back and forth between, around 0. to a harmonic series. And this series is convergent. Is convergent, but not absolutely convergent. Right, because if you slap absolute value sign, you get the harmonic series, and we already know that this is not convergent, but not absolutely convergent. Okay. So this is the alternating harmonic series. Okay, now let's try to prove that absolute convergence implies convergence. And so I'm going to look at, so I take two series. So I have Sn, that's my original series. Ai, I equal to 0 to n, like that. And then I take the one where I slap absolute value sign and I denote it with a bar. So I equal to 0 to n of Ai. And then I make a little observation. And the observation is that if I'm looking at Sn and Sm, so just think about at n here is larger than n, then you can think about this thing here as this thing here is just where you're summing from m plus 1 and up to an, right? That's this difference, right? But if you take absolute value on this, absolute value on that, well, that's of course less or equal to, right, where you're taking absolute value on each individual one. Like that, right? But this thing here is just, right, this thing here is just for the other series, this series. It's the same sort of difference. And here, actually, I don't even need to take absolute value, but I could take absolute value, but this is already non-negative. And so you see that, so you make this little observation, but now we know that if it is absolutely convergent, then this sequence here converge. So this means that in particular, what's equivalent to saying that it's a Cauchy sequence. And so this means that things, if you are sufficiently far out, these things here bunch together, epsilon together, if you are bigger than some capital N. But now this inequality say that these things here bunch together. So you see that if this is convergent, then it's a Cauchy sequence, but this means that this here is a Cauchy sequence. So it means that the original series was convergent. Right? Okay. And so now let's look at one more example, and then we'll talk about some of the tests. Yeah, so let's look at, so we saw that the harmonic series is divergent. So we saw that the harmonic series is divergent, but what about, right, I mean, and what about, so there's another thing you could do, right, so maybe the most important series is the geometric series. After that, you can debate a little bit which series is the most important. But these here is some other candidates for that. So I'm looking at now the sum here, n equal to 0 to infinity. And I'm looking at 1 over n squared. but you could do it more generally where you raise it to some power. Right? If that power was 1, you got the alternating, you got the harmonic series. But now I'm just looking at a specific power 2. Okay. And so I claim that this series here, this one doesn't really have a name, but it is a key series. And so I claim that this here is convergent. So this is. Now, you observe that the AN, in this case, this is just 1 over n squared, right? And these here are non-negative. So all we need to do is, we just need to prove. So this is, when the ANs are non-negative, all you need to prove is that the sequence, you just need to show that the Sn, which is where you're summing here, I equal to, you shouldn't sum from 0, you sum from 1, I equal to 1 to n, that you will need to prove that these here are bounded. Right? This is because the ANs are non-negative. Okay, so now the idea here is that, again, this is not necessary how I would do it, but the advantage with this here is that it doesn't use anything fancy. I mean, it's not like the way later on you do it, you will use the integral test, but we haven't talked about this integral test yet. So you can do it very simple-minded. And so the claim here is that that you want to compare. So we want to make a following claim that if you're looking at s to the 2n plus 1, sorry, f to the 2n, so it's just similar to what we did before. If we want to prove that this thing here for this series, that this is less than the sum here from I equal to 0 to n of 1/2 to the power I. So we'll prove n to n minus 1. So we claim this thing here. Now you see that, so we claim that we have this inequality for all n, right? But this thing here, we already know that this here is a geometric series. With C equal to 1/2, so it's convergent. And you see this thing here is a subsequence, but it's a subsequence because this here is convergent. This here is bounded by something fixed, right? So this means that this subsequence here is bounded. But the original series was a monotone increasing sequence. So if a subsequence is bounded, then the original sequence is bounded and so convergent. Right? So we just need to prove, just need to give a bound like this. And the bound here you get is, by we already determined that this here is less or equal to 1 over 1 minus C. C is 1/2. So this is like this. So this here is 1/2. So this whole thing here is 2. So this here would be bounded by 2. Right? Okay. So now we want to prove. So we want to prove this claim here. So if we can prove this claim, then we have that the series, this series here, is convergent. Okay. So now let's try to do that. So when n is equal to 1, So we do it again in the same way. This is called by induction. We do it first for n equal to 1. For n equal to 1, it is a claim that S, right, if n is equal to 1, this is 2 minus 1, that's 1. So it's a claim that this thing here is bigger equal, is lesser equal to. And now it's, when n is equal to 1, it's just, this is, you're just summing over one thing. It's just one thing, and it is a half to the power 0, and that's 1. So for n equal to 1, this is what we need to show. Okay? But now let's see, for n equal to 1, well, this here is indeed 1, so that's okay, right? So this is okay. So now assume that s to the power 2n minus 1 is bounded by this I equal to 0 to n minus 1 of 1/2 to the power I. Right? So assume this, and we want to prove the same thing, but for n plus 1. So want to show the same inequality for n plus 1. Okay? So let me do that. So I'm looking at S2n plus 1 minus 1. So S2n plus 1 minus 1, I can write as where I'm summing the first 2n minus 1, and then I'm summing, and then plus, and then when I'm summing from I equal to 2n to up to 2n plus 1 minus 1, right? And then it's 1 over I squared. Now in this case, remember before we wanted to prove that something was divergent, so we wanted to give a lower bound. In this case, we want to give an upper bound. So when we do this, we think about what is the, instead of what is the smallest, we think about what is the largest of these numbers. But that's the first one, right? And there are, again, just like before, there are 2n many of them. So this thing here is less or equal to S2n minus 1, sorry, yeah, like this. And then there are 2n many, they're all non-negative, and this is, and the first one is the largest. So 1 over 2n squared, like this, right? And so you see that this thing here is, so now we can fill in the assumption. We were assuming that this here was less than this. This is the sum from I equal to 0 to n minus 1 of 1/2 to the power I. And this thing here, but the square kills that one, and you're still left with 1 over 2n. But you see, this is, of course, exactly the next one in the series. So this is I equal to 0 to n of 1/2 to the power I, like that. Right? And that's indeed, this is like the induction step, right? Right? This is what's called the induction step. So this is, so it's true also. So if it's true for n, the claim, then it's also true for n plus 1. Okay. So now So now, I have just 4 minutes left. There's a little bit more I already posted the lecture notes, and there's a bit more here I want to talk about. So I want to talk about some of the tests, but we'll talk about that more next time also. So to determine whether or not a series is converge, then there are a number of tests. And then, of course, the key point is to use the right test. So I will just talk about, so I just mentioned some of the tests, but we won't anyway go through all of them now. So maybe I can't go through any of them. So there's a comparison test. There's a ratio test. There's root test. And there's also the one I talked about several times, the integral test. And then there's even one called the alternate series test. Okay, now maybe I can just talk about the comparison test. That's in a way the simplest of them. And so the comparison test is that you're looking at two series. So you have these two series here, and you have this other series here. And the comparison tests say that if you have an bigger or equal to 0, less or equal to bn, so if you have this and the bn, this series here, converge, then the corresponding thing with the an will also converge. And this is the simplest version of the comparison test. And this is, in a way, used in two ways, right? So you have a series, and maybe it could be a super complicated series. And but you see some kind of pattern in, and so you can compare it with a much simpler series that perhaps you already know whether it's converging, right? And so if you can compare it with something else, and you know that that's converge, then you conclude that AN series is converging. It's also sometimes used that you want to determine whether this series here is converging. But you can easily kind of compare it with some other series where you have this relationship here, and this one you already know is divergent, right? So it's used in both ways, right? It's used to both determine that a series is convergent, and it's also used to determine that the series is divergent. Okay. So there's a little bit more about tests in the lecture notes, but we will anyway talk about it more next time. Yeah.
I have a question about like the intuition of this, like S sub 2n.
Yeah.
Like where are you getting it?
Right. So that's right. So that sort of thing is, I mean, this last one show you that the geometric series is one that sort of come up often as a kind of comparison in a way, right? How you get it different for different people. Obviously, you don't start with a claim. You're sort of looking at the first few things and you see a pattern, basically. But it's not, I mean, this is not the way you want to really, later on, I would never prove any kind of convergence like this. There's a way of comparing it with the So the idea is, let me just tell you, but of course the lecture is over. But there is, so the integral test is that you're looking at, so you're looking at a series, and if you have a series of non-negative numbers, you can think about that the series is like the area below. If this here is, think about this here as A1, and this is maybe A2, then you can think about the sum as the sum of the areas like this. And so the integral test is that you're comparing it with some curve and the area that lies below it. Then it's like much more clear. Right? The other one is like where you have to do it case by case. Right? There's not, here there's a kind of general idea. So it's nice in this particular case. I'm not sure it's, what I mean? I mean, you have to look at the first few things and see if you see a pattern, right? And of course, you don't start with a claim, right? That's like the end. When you actually have a claim, then you already know what's going on, right?